Large language models, they're really everywhere now, aren't they? And making them consistently helpful and safe, that's still a huge ongoing challenge.
It absolutely is.
And right at the heart of guiding how they behave, we've got these things called reward models.
Mm-hmm.
But the traditional ones, they often hit some pretty big hurdles.
Yeah, like scalability for one.
Yeah.
It's just incredibly tough getting enough good human preference data, high quality data.
Right. And then there's generalization. They can be susceptible to reward hacking.
That's a big one. And they often don't perform so well on tasks they haven't seen before.
Even things like rule-based verification, which can be useful sometimes.
Sure, for certain tasks.
It just doesn't really work for those really open-ended creative jobs, you know?
No, it falls short there. The challenge of making LLMs reliable, adaptable,
Mhm.
it really highlights this critical need for, well, a fresh approach to shape how they behave.
Yeah.
The sheer amount of data, the subjective human input needed for traditional methods, it creates these real bottlenecks.
And that's exactly where we're heading in this deep dive. We are focusing on something called Policy Discriminative Learning, or POLAR.
Polar, yeah.
It's a new solution proposed in the paper. Pre-trained policy discriminators are general reward models.
A really interesting paper.
So the mission for you, our listener, is to quickly get a solid understanding of this innovative approach. We want you to discover some maybe surprising insights about what it can do and grasp why it matters for the future of LLMs.
And hopefully without getting bogged down in too much jargon.
We'll try our best. Okay, so let's unpack Polar's core idea. It kind of reframes what a reward model is. It's not about giving an absolute score, like this response is a 9 out of 10. Instead, it acts as a policy discriminator.
So what does that mean, policy discriminator?
Well, it quantifies the difference between the policy the LLM is currently using, what it's doing now, and the desired target policy you want it to reach.
Oh, okay, so it's relative.
Think of it less like a fixed scorecard, maybe more like a compass guiding the LLM towards where it needs to go.
That's a good way to put it. What's really fascinating here is how this perspective shifts the whole game. You move away from rigid, absolute criteria
Right.
to capturing these relative differences between policies.
Yeah.
And this becomes a much more scalable, kind of high-level goal for optimizing the LLM.
Scalable how?
Well, it's particularly good for modeling those complex ranking relationships we see in human preferences, which is quite different from older methods that often needed manually defined, sometimes brittle criteria.
Okay.
So this allows the reward signal to guide the training policy towards the behaviors we want, but maybe in a more flexible way.
So if Polar's goal is learning these relative differences, how does it actually learn them? What's the training setup look like?
Right, so Polar uses this really interesting two-stage approach.
Yeah.
The first stage is unsupervised pre-training.
Unsupervised, okay.
Yeah. And in this stage, the reward model learns what the paper calls criterion-agnostic policy differences.
Criterion agnostic, meaning?
Meaning it's not tied to one specific goal yet. Imagine it's like learning the unique fingerprint or style of different ways an LLM might operate.
How does it do that?
It looks at trajectories,
Yeah.
sequences of text generated, and learns to tell the difference between ones that came from the exact same policy versus those that came from different policies.
Oh, okay.
And it trains on this huge synthetic data set generated from lots of different LLMs. It uses a contrastive learning objective.
Contrast of like comparing things.
Yeah, essentially comparing and distinguishing these policy fingerprints. And this foundational learning is really, really key for its ability to generalize later on.
Okay, so it builds this general understanding first. Then how does it get aligned with what humans actually, prefer?
That brings us to stage 2, supervised fine-tuning.
Supervised, so human input comes in here.
Right, but efficiently.
Right.
This stage adapts that pre-trained model using human judgment, but it only needs a pretty small set of reference examples.
Reference examples, like good answers.
Could be. They can come from human annotations, or even just outputs from other high-performing LLMs. And alongside those, you have candidate examples that have been ranked by humans.
Ranked, like, this one's better than that one.
Exactly. And crucially, even if all these examples initially came from just one LLM policy, the human evaluations naturally impose different criteria, different judgments.
I see.
So this allows the model to align its policy discriminating skills with our standards. Basically, it learns to judge new responses by comparing a candidate against a known good reference.
Okay, that makes sense. Now, this is where it gets really interesting for me, the results. The paper talks about Polar showing significant improvements in just evaluating
Oh,
preferences.
definitely. The numbers are quite striking.
Like Polar R7B, that's the 7 billion parameter version. It improved preference accuracy from around 55% to 81% on STEM tasks,
Yeah, huge jump.
and from about 58% to over 85% on creative writing tasks. Compared to the previous best methods, that's a massive leap.
It really is. And what's particularly striking is the efficiency behind those numbers.
How so?
Well, that Polar 7B model actually performed better than a state-of-the-art 72 billion parameter model, World PM, I think it was
The
called.
72 billion.
Yeah, Polar 7B beat it by almost 6 percentage points, despite being roughly 10 times smaller.
10 times smaller, but better performance.
And even the smaller Polar 1.8B model achieved really competitive results at just a fraction of the size, sometimes like 115th or even 140th the size of the bigger baseline models.
So it's not just about size then.
No, it really showcases this robust, out-of-distribution generalization. And that seems to be a direct result of its unique pre-training stage. It suggests the learning strategy, the quality of it, can really trump just throwing more parameters at the problem.
So Polar is great at evaluating preferences, but does that actually translate into making the LLMs themselves better through reinforcement fine-tuning, RFT?
Yes, that's the crucial next step, right?
Yeah.
Does it help in practice? And the answer seems to be yes. They observed concrete improvements in the policy models themselves.
Like what kind of improvements?
Well, for instance, Llama 3.18b, its average performance across 20 different benchmarks went up from about 47% to over 56%.
Okay, that's a solid gain.
And another one, Quen 2.53db, saw an improvement from roughly 64.5% to over 70%.
So it works for different models too.
It does. It shows that these polar reward models are providing more accurate, more reliable signals for the learning process, which contributes directly to better generalization for the LLMs being trained.
That makes sense.
And actually, there was an interesting observation here too. While the smaller 1.8b and the 7b polar models performed kind of similarly in the preference evaluation tests,
Right, you mentioned that.
the larger 7b model showed a noticeable advantage when used in these downstream reinforcement learning applications.
Huh. So the preference evaluation didn't tell the whole story.
It seems that way. It suggests that those standard preference evaluations might not fully capture all the nuances needed for really effective policy optimization during reinforcement learning.
That's a really important point. Another fascinating thing mentioned was scaling laws. Polar apparently shows scaling laws similar to what we see in the big LLMs themselves.
That's right, which is quite exciting, actually.
Why is that so exciting?
It means there's a very clear, predictable power law relationship. As you increase the computation or the model parameters for Polar,
You get better results.
you see a predictable decrease in the validation loss. So yes, better performance. And the correlation they found was incredibly tight. The R-squared values were close to 0.99.
Almost a perfect correlation.
Almost perfect, yeah, for both scaling up model parameters and scaling up the optimal training compute.
So what does that imply practically?
It suggests a highly reliable, consistent return on investment. If you scale up Polar, you can be pretty confident you'll get predictably better results. It makes its future development much more, well, predictable.
Okay, that's powerful. Now, speaking of what makes Polar work, the paper also did these ablation studies, where they basically remove parts of the system to see what breaks, right?
Exactly. They're key to understanding why it works so well.
So what did those studies find? What parts are most important?
Well, first, they show just how crucial that pre-training stage is.
The unsupervised part we talked about earlier?
That's the one. Models that were only fine-tuned skipping the pre-training,
Hmm.
they did okay in the preference evaluation tasks.
Okay.
But their performance dropped significantly when they were used for the actual RLHF training, the reinforcement learning part.
Ah, so the pre-training isn't just for generalization, it's critical for the RL step too.
It seems essential for making it an effective guide during reinforcement learning. It really builds that necessary foundation.
Got it. What else?
They also found that even if you didn't do the pre-training, just having those reference trajectories during fine-tuning still provided really crucial guidance.
The good examples.
Yep. Having those simplify the reward model's job, its evaluation task,
Right.
and it led to more stable training for the policy model. It's kind of like, having a good example to compare against just makes learning easier.
Makes sense. Anything else from the ablations?
One more key finding. Reinforcement fine-tuning using these polar reward models significantly outperformed just doing straightforward supervised fine-tuning on the same preference data.
So using Polar as a guide in RL is better than just training the LLM directly on the good examples.
Substantially better, according to their results. It clearly demonstrated that these polar reward models act as really effective graders or guides for the whole policy optimization process. They do more than just represent the preference data.
Okay, so pulling this all together, what does this Polar approach really mean for you, our listener? It seems like it offers a genuinely new and potentially very scalable way to handle reward modeling.
I think that's fair to say. It shifts the focus from judging absolute quality to discerning these relative policy differences.
And the results look impressive. Strong performance, good generalization even with smaller models, and these clear scaling properties.
Yeah, it certainly makes it a very promising direction for developing more general, more robust reward models for LLMs in the future.
It really does open up some fascinating possibilities, doesn't it?
It does. Think about it having a reward model that can pick up on subtle differences between policies and adapt flexibly.
Right.
It raises an interesting question for you to ponder. How might this ability, the ability to define target behaviors more, maybe arbitrarily, rather than needing exhaustive human labels for everything, how might that accelerate developing more diverse, more specialized AI assistants? Could it let us explore more nuanced criteria, things that are really hard to define explicitly with just labels?